So in today's session, we're going to go through all of the different topics that could turn up on tomorrow's first chemistry exam. Unlike the biology, there haven't been any topics taken out at all, so every single topic that you've learnt about could come up in the exam. The green slides are to tell you which topics the exam board have said are really important ones that are definitely worth a lot of marks, but the other topics that are on purple slides could still come up, but they can only really come up as 1 or 2 mark questions. But obviously those can still add up to make quite a lot of it, so we are going to go through and revise all of them. Before we get started on the actual chemistry, a few little last minute bits of advice. The first one is that you have to write in black pen because your paper is going to be scanned. So if you don't have a black pen, come find one of us in the morning and ask. Don't wait until you're inside the exam because the invigilators aren't going to have lots and lots of spares. Likewise, because your paper is being scanned, make sure that you're only writing inside the box. Watch out for any sneaky units, so things like where they've put a mass in milligrams or things like that. It's a really good idea to answer the long questions in the form of bullet points. Remember, there aren't any marks at all for writing in full sentences or paragraphs. So if you can keep yourself really concise, it's just going to make it way easier for your examiner to follow. So go ahead and do that. If you've got any question that has the keyword, the command word, evaluate, then you have to write a conclusion. So usually you're going to be putting advantages and disadvantages of 2 different things, and they usually set up the question so that either one of them could be right. You just need to pick one and say why it's the best one, but you have to write a conclusion or you can't get the last 2 marks. And also, especially for these required practicals, make sure that what you're writing has a sort of logical flow to it. So imagine that somebody who'd never done the practical was going to need to follow your method. Would they actually be able to, and would they be able to answer the question at the end? Now, quite a lot of the marks are for these working scientifically skills, so things that aren't biology, they aren't chemistry, they aren't physics, but they're just about being a good scientist. So do you know your variables? So the word to remember is mixed-dry, and that stands for you modify the independent variable, and if you're drawing a graph that goes on the x-axis, and then the dependent variable is the thing that you record, so you're observing it, you're measuring it, and you're writing down to see how it changed, and that would go on the y-axis. I'm a control freak, so I like to control things and keep them the same. So your control variables are things that you keep the same to make it valid or to make it a fair test. And just watch out, we're only talking about temperature being a control variable if you're actually doing something to change it. So if you do an experiment in a water bath, then temperature might be a control variable, but just doing it at room temperature isn't enough. If I do an experiment myself again, so if it's me doing it, that's repeatable. So it's you doing the exact same thing in the exact same way and you get the same pattern again. Remember, it's the pattern that's important. It's not the exact numbers, but just did you see the same general trend? And if you do the experiment, so if it's someone different doing it or they're doing a slightly different technique, then that's reproducible. So for instance, if I was looking at the temperature changes when I added different metals to copper sulfate, and I found out that the most reactive metal was always the biggest temperature change, and I did it again and I still found the most reactive metal was the biggest temperature change, that's repeatable because it's me repeating it. If somebody else then tried adding acids, adding the same metals to acid instead of copper sulfate, it's a slightly different experiment, but they find that it's still the most reactive metal that gives the biggest temperature change, then that's reproducible because it's a slightly different method and it's different people doing it. The resolution of your equipment is the smallest measurement that you can tell the difference between. Computerized methods are good because they're accurate and rapid and sensitive. And remember, if you draw a graph, then the line of best fit doesn't have to be straight. I know it does in maths, but in science it doesn't. So if your data are giving you a nice curve, you need to draw a nice curve through them. Errors are the things that are going to mean that you don't get exactly the same number every time you do an experiment. So we've got 2 different kinds. We've got systematic errors, and that's basically where there's a problem with your equipment. So it's always reading slightly light or it's always reading slightly heavy. And basically you figure that out by figuring out how much it's wrong by and adjusting. So if your scales were always reading ½ kilo light, then you just add on ½ kilo. And then random errors are where your equipment isn't being very precise, and so it's kind of, you're getting the numbers and they're all clustering around the same point, but they're slightly lower and slightly higher. And so basically you repeat more and then you calculate what the mean is. Now we can get going with the chemistry. So we start off with atomic structure. This is our first topic out of the 5 topics we've got to cover. So firstly, we say that everything in the world is made up of atoms, and those are the smallest parts of an element that can exist. There's about 100 different elements, and we can find them listed in the periodic table. So you do get the periodic table in your exam, but you don't need to know that there's exactly 118. You just need to know about 100. Those elements can then react together to form compounds, and a compound contains 2 or more elements, and we say they're chemically combined, which just means bonded in fixed proportions. So in other words, we could put a formula like H2O, and that tells me there are always 2 hydrogens to 1 oxygen. You should be able to name compounds if they ask you to based on the formula. So if there's just 2 elements in the compound, then there's going to be a metal and a non-metal that you're going to need to look at. The metal is always first, and you just keep that word as it is. And then you take the first syllable of the non-metal and you put "ide" on the end. So some examples of that might be iron oxide, so the iron stays as it is, and then we've got ox from oxygen and then "ide." Copper chlor, so the chlor from chlorine, ide, and tin sulfide. If we've got 3 elements, then the third one is going to be oxygen, and the kind of secret chemistry code for oxygen is 8. So you do exactly the same as you did before, but instead of putting ide on the end, you put 8. So for instance, copper sulfate, if we didn't have the oxygen in there, it would be copper sulfide, but we do, so it's copper sulfate. And then silver nitrate and aluminium phosphate. So each time we've got that 8, which tells us that there's oxygen hiding in that compound. So the next part of the GCSE is about separating mixtures, and we can do this by using physical processes. So things like heating or cooling or filtering, which allow us to split up the different parts of the mixture, but they're not actually changing any of the chemicals that are in there, we're just splitting them up. So there are 5 different techniques that you need to know about. We start off with filtration. So we use filtration for splitting up an insoluble solid from a liquid. So for instance, sandy water. Then crystallization, which you use in the required practical. That's when we want to separate out a soluble solid from the liquid. So for instance, making copper sulfate crystals out of copper sulfate solution. Then distillation, simple distillation and fractional distillation, they're both going to use state changes. So basically we're heating something until a liquid evaporates, and the difference is that with simple distillation we're just trying to remove one liquid from another one, but with fractional distillation we've got a whole different mixture of liquids, and because they've all got different boiling points they can be separated at different points in this fractionating column. And finally, we've got chromatography, which is more of an analytical technique, but again, we can use it to separate liquids. And obviously that comes up a lot more in paper 2. So just to give you a tiny bit more detail about fractional distillation, we're using this fractionating column. It's going to be very, very hot at the bottom of the column and cooler at the top, which is what we call a temperature gradient. And basically what happens is that the mixture of liquids all evaporate at the bottom, and then as they rise up further and further away from that heat source, they condense when they reach their boiling points. And as each gas condenses, it turns back into a liquid, and then it can be separated out. And it's useful because it allows us to have all of those liquids afterwards and we can use them. We often use chromatography when we want to analyse mixtures of liquids like colours in an ink, and we're trying to see what's in there. So basically what we're doing is we have a series of what we call standards, which are things that we already know what they are, and we're comparing our sample to that. And basically we're separating them out according to their retention, so how well they are retained by a stationary phase, which here is the paper, while a mobile phase, which here is the water, is passing through it. So for paper chromatography, the retention links to the solubility, but this is really more of a paper 2 topic. For paper 1, they're just likely to ask you when you would use it rather than wanting you to get into the nitty-gritty of how you do it. So then when we get the results from the chromatography, you're going to have anywhere that there is a pure substance, you just get a single spot, and basically you can line these up. So in my sample here, I've got a spot that lines up with A, so that tells me that A was part of the sample, and I've got a spot that lines up with B, so that tells me that B was in there, but the other spots like C and D, I don't have anything that lines up with them, so therefore those were not in my sample that I was analysing. So it's kind of a comparative technique, like how you would use fingerprinting. So a fingerprint doesn't tell you who was there and who touched your stuff, but if you have other fingerprints to compare it to, you can say, oh, these two match up. So next up, we get onto our real atomic structure. So this is common content with physics. You're going to need it for both exams. You need to be able to describe the modern model of the atom that we use now, and then we're also going to get into a little bit of a history lesson about how we got here. So if I was going to describe this atom now, I'd be talking about the fact that there is a small, dense nucleus, and that contains the protons and the neutrons. So remember, N for neutron, N for nucleus, and then P and N are close together in the alphabet, so they go close together in the atom. And then around the outside, in the shells, we've got the electrons. Now for each one of those particles, you need to be able to say where they are and also the relative mass and the relative charge. Remember, it's really important, as soon as you see the word relative, you have to put a number on it. So if they ask you for the relative charge and you just say positive, then that's wrong. Relative means it has to be as a number. So the relative charge of a proton is +1, relative charge of an electron is -1, relative charge of a neutron is 0. And then for the masses, proton and neutron are 1, they have the same mass as each other more or less. And then for the electron, we just need to say very small. If you've got a number in your head and it's right, that's fine, but the specification just says very small, so you don't have to be any more detailed than that. If we want to know how many protons and neutrons and electrons there are, we can look at the periodic table square. So remember, you have that periodic table for the exams. It has a key that tells you what these numbers are. So at the bottom it says atomic brackets proton brackets number. So you know that the number of protons is the bottom number. So here it's 3, I've got 3 protons. The top number is the mass number, and that tells me how many things there are in the nucleus. So there are 7 things in the nucleus, and then the bottom number has told me that 3 of them are protons, so the other 4 must be neutrons. And then for an atom, the number of protons and electrons is the same, so I've also got 3 electrons. But that's only for an atom. Remember, when we get to unit 2 and the ions, it's going to start changing. You should note that overall the radius of an atom is approximately 0.1 nanometers, and you are supposed to know that in standard form for meters as well, so 1 times 10 to the minus 10, and the nucleus only makes up 1/10,000th of the radius of that atom. So even though I've drawn it really big here, in reality you just wouldn't even be able to see it on this diagram. Then we can talk about isotopes. So isotopes are atoms of the same element that have the same number of protons, but they've got different numbers of neutrons. So this is going to mean that chemically they behave exactly the same, they form compounds in the same way, they do chemical reactions in the same way, but physically they're a bit different to each other. So my lithium atom at the bottom here would be heavier because it's literally got more neutrons inside it. And you need to be able to calculate the relative atomic mass if they give you a mixed sample. So they might say something like, how much would the relative atomic mass be in a sample with 90% lithium-7 and 10% lithium-9? So all you need to do is work out what is 90% of 7, what is 10% of 9, and then add them together. So personally, I like decimals, but if you wanted to do 7 divided by 100 and then times by 90 to get 90%, that's fine. Whatever method you like for percentages, you just crack on and do it. So 90% of 7, 10% of 9, add them together, we get 7.2. You want to do a little common sense check. You're going to end up with a number that is between the numbers you started with. So I started with 7 and 9. I can't get an answer of 16, say. If that happens, I've done something wrong. It's got to be between those two numbers, and it's going to be closer to the one there's more of. So it's closer to 7 because I've got 90% of the 7. Then we get a little bit of a history lesson. So thinking about how have models changed over time? We know that scientists do experiments, they learn more, and they update their models. So first off, we have Dalton. And we have his model where he thought that atoms were, he called them small indivisible spheres. So indivisible, not invisible. So he didn't say you can't see them, he said you can't divide them. And in fact, he compared them to billiard balls. So kind of like snooker balls. Then we had J.J. Thomson and the plum pudding model. So he discovered that electrons were a thing, and so he imagined that the atom was a bit like a Christmas pudding, only it was a plum pudding. So instead of having those sultanas stuck in your Christmas pudding, those are the electrons, and then he thought all the rest of it was just this big positive mass. Then we have Rutherford. Now he's the only one where you need to know about the experiments that he did, and this is called the alpha scattering experiment. So he managed to work out with this alpha scattering experiment that we had this positive mass that was concentrated right in the centre in the nucleus, and the rest of the atom was actually empty space. So how did he do it? So the experiment is called the alpha scattering experiment, and what he did was take a really, really, really thin sheet of gold foil and fire alpha particles at it. Now most of them, absolutely almost all of them, went straight through. It's important that you're saying most, not just some, and the point is that most of the atom is empty space, so they just went straight through. And then a very, very few of them were really strongly deflected, so they bounced off, and that told us that the mass was concentrated in the centre. There was something small and hard that was bouncing off a few of them. And because we already know that alpha particles are positive, the fact that the nucleus was repelling them meant that the nucleus was also positive, because you've got that idea from physics about opposites attract and things that are the same as each other repel. So the fact that the positive alpha particles were repelled, that means that the nucleus was positive too. Then we had Niels Bohr, and he worked out that electrons weren't just going wherever they wanted to, they were orbiting the nucleus at fixed distances, and he did sort of some mathematical calculations, and then it turned out that those sort of joined up, they squared up with the experimental data we had. And then around the 1920s, protons were discovered, and then the last bit you need to know is that in 1932, James Chadwick discovered the neutron. And that was important because we had some mass data about elements that didn't really make sense. So like, you know that chlorine has a mass of 35.5, and people were going, well, how can that be a thing? Because you can't have half a proton. But it's because we had these different isotopes, and so you have chlorine 35 and chlorine 37. And so what we were seeing was kind of an average of those masses. Okay, so this is our first major topic. This is one of the ones the exam board has said is going to come up, the periodic table. And this is a really, really big topic. So when I first heard periodic table, I was thinking, oh, that's not too much to worry about. But actually this contains all of the different groups as well as part of that topic. So alkali metals, halogens, noble gases, they are all part of this topic. So the first thing to know is you are going to get the periodic table in your exams, and it does have a key on it like this. So it does tell you that the bottom number is the atomic number, which tells you how many protons are in it, and the top number is the relative atomic mass. So for the periodic table, you need to know that the vertical columns are called groups. So we start with group 1 on the left, and then group 2 all the way through to group 0 on the right hand side. And the way that it was decided which element goes in which group is how many electrons they have in their outer shell. So everything in group 1 has 1 electron in its outer shell. Everything in group 2 has 2 electrons in its outer shell. And then the periods are the horizontal rows as we go across. And this is about how many shells there are. So when you're trying to do your electron configuration, when you're doing your little dot and cross diagram, remember, the group tells you how many go in the last shell, and the period tells you how many shells there are. So say if I was drawing potassium here in group 1, it's in the 4th row down, because don't forget that there's that first row with hydrogen and helium. So it's got 4 shells, and then the last shell has got 1 electron in it. So when we're thinking about where the different elements in the periodic table are, obviously elements that are quite similar are put together. And the first big distinction we can make is about metals versus non-metals. So you've got used to drawing that little staircase, and you might have drawn it here in the green or here in the red. It doesn't matter which one you do, because for your GCSEs, you're not going to be asked about anything that is very close to that staircase. We don't do the semi-metals at all. So you don't need to worry. You just kind of need to know metals on the left, non-metals on the right. So it's going to look a little bit like this. And then also don't forget that the one that is a little bit weird and different is hydrogen. It sits out on its own up here, but it is a non-metal. So the important thing about these metals is that they form positive ions. So in other words, they lose electrons to leave a little charged particle called a positive ion. Metals are malleable. In other words, they can be bent or hammered into shape. They are conductive, so they're good conductors of electricity and of heat, and also they have high melting points. And another bit of the spec goes into why do they have each of those properties. Then we get another little history lesson. So the periodic table hasn't always been laid out the way that we use it now, and that's because when it was first developed, subatomic particles hadn't been discovered yet. So we couldn't just put all of the elements with 1 electron in group 1 because we didn't know what an electron was. So to start with, they were just kind of put in order of their atomic weight, because actually 9 times out of 10 that gets them in the right order. But it did lead to a couple of problems, because although it almost always works, there are exceptions. So for instance, potassium and argon, they'd be the wrong way round. So you'd have potassium, which is super reactive in the middle of the noble gases, and argon, which is, you know, a noble gas, so it's inert and it doesn't react with things in with the alkali metals. And obviously that's not right. And also there were some elements that were missing. So it's actually really hard to find elements, because usually in nature they're in the form of compounds, and so they look different and you can't identify them as elements. So the initial drafts of the periodic table weren't perfect. So the best version before the modern one that we have now was the version that was created by Dmitry Mendeleev. So he's this really famous Russian chemist. And what he did was say, I'm going to leave some gaps because maybe there are some elements that haven't been discovered yet. But crucially, he also made predictions about those. So he left a gap, but he said, I think in a few years' time, someone is going to find an element that belongs here, and it's going to have a mass of about this, and it's going to have a melting point of about this, and it will fill in that gap. So because he'd made those predictions, when a few years later people did discover those elements and they found that the predictions were right, they were able to kind of validate his periodic table and say, actually, yes, this is a good periodic table, this is good science that he's done. So then, as we said, there are a few different groups that you need to know a little bit more specific information about. You should know that all of the elements that are found in group 0 are called the noble gases, and noble just means unreactive or inert. So these elements don't really form molecules because they've already got this really stable arrangement of electrons. So they have a full outer shell. Helium's got 2 electrons in its outer shell because it's in that first period, so there's only room for 2. And then all the rest of the noble gases have 8 electrons in their outer shell. And that's a really stable conformation, so they don't need to give or receive electrons to become stable, so they just tend not to form molecules. You also need to know that as you go further down the group and the atoms get bigger, the forces between them get stronger, so the boiling points go up. But all of them still have boiling points that are below room temperature, so therefore they're all still gases. Then we've got the alkali metals, which are these really, really soft metals. You can literally cut them open with a scalpel. And you should know that the alkali metals are highly reactive, and they all have 1 electron in their outer shell. That's why they're in group 1, and they lose that in order to do chemical reactions. Now, because as you go down the periodic table, the atoms are getting bigger, that 1 electron that needs to be lost is getting further and further away from the nucleus. So it's easier and easier for it to be lost because the nucleus is kind of hanging on to it, and the further away the electron is from the nucleus, the easier it is to get rid of it. So that means that as you go down the group, the elements become more and more reactive. You need to know a bit about how they react with oxygen and with chlorine and with water. So metals react with oxygen to form metal oxides, and what you see for that is just that the metal stops being shiny and it kind of tarnishes and gets darker instead. Reactions with water you've almost certainly seen live. So when you put the alkali metals in water, they form lots and lots of bubbles because they're releasing lots of hydrogen. And you'll probably see the metal moving around on the surface of the water, and the more reactive it is, so the further you go down the group, the more bubbles it will produce and the faster it will move. Lithium and sodium don't tend to sort of set themselves on fire or anything like that, but by the time you get to potassium, you may see it igniting the hydrogen, and if it does, it burns with a pretty lilac flame. And also, when they react with water, they produce a metal hydroxide, which is just another name for an alkali. Now, if all you've got is the metal and the water, you won't see anything to tell you that. But if you put universal indicator in, then that would go sort of bluey purpley colour, or you could use a different indicator as well. And then in terms of those metals reacting with chlorine, these are silvery metals. Chlorine is a greenish gas, and when they react together, it's quite an exothermic reaction. It produces a really bright light, and at the end of it, you get sort of white crystal powder. So an example would be sodium chloride. That's a metal chloride that would be made from this reaction. So you're going to see something that looks a bit like salt. Then the last group that you need to know about for this topic is group 7. So again, we've said they're in group 7 because they have 7 electrons in their outer shell, and these are called the halogens. So they make these little molecules that contain 2 atoms covalently bonded together. So they go around as little pairs of atoms. So they look a bit like this. You've got your dot and cross diagram, which we'll get to in Unit 2 in a second. So if you think about the alkali metals getting more reactive as you go down the group, the halogens do the opposite. So they get more reactive as you go up the group, because when the halogens react, they don't lose an electron, they gain an electron. So for them, the smaller the atom is, the closer that incoming electron is to the nucleus, so the stronger the force of attraction that it feels and the easier it is to gain it. Like how we had with the noble gases, as you go down the group and the atoms get bigger, the forces between them are going to get stronger and the forces between the molecules are going to get stronger. So therefore the boiling points and the melting points are going to increase. And so that ends up meaning that the first two halogens are gases, bromine is a liquid, and then the last two are solids. So that's one topic down, 4 more to go. So firstly, we need to know that there are 3 types of strong chemical bond: metallic bonds, ionic bonds, and covalent bonds. And when we're trying to figure out which type of bond it is, we need to look at where the elements in a substance are in the periodic table. So if we put our staircase back in there and say we've got our non-metals on the right and our metals on the left, if we've got just metal elements, so say if we had magnesium or iron or gold, we're going to see metallic bonding. If we've got just non-metal elements, and that does include hydrogen as well, then we're going to see covalent bonding. And if we've got a mixture of metals and non-metals, that's when we get ionic bonding. So metallic bonding first. In metallic bonding, you have these regular rows of positive ions, and they're surrounded by a sea of delocalized electrons. And delocalized just means the electrons don't belong to a particular atom, they don't have to stay with it, they can move around everywhere. So those together form a giant metallic lattice. Giant isn't just me using a different word for big, it's sort of the technical term, you need to say giant. And this whole lattice is held together by a strong electrostatic force of attraction between those positive ions and the negative delocalized electrons. Another one of these major topics is all about explaining why substances have the properties they have. So metals conduct electricity because they have those delocalized electrons which aren't tied to one particular atom, they're free to move. So we want to say that they're free to move and carry charge through the metal. So there's my little electron moving. And likewise, they can conduct thermal energy for the same reason. So those electrons are moving around and they're carrying the energy with them, basically. Then to explain the high melting points of metals, we kind of need to think about, well, what is a melting point and why do you have one? So all pure substances can be a solid or a liquid or a gas, and what state they're in at any time just depends on what the temperature is. So, you know, even oxygen could be a solid, even iron could be a gas. It just depends on the temperature. So we call the temperature where a solid turns into a liquid the melting point, and we call the temperature where a liquid turns into a gas the boiling point. And the particular temperature that it is going to depend on how strong the force is between the particles. So if you've got really, really strong forces holding things together really tightly, it's going to need a lot of energy to overcome those forces, and therefore the melting point will be really, really high. Whereas if you've got really weak forces and it's really easy to overcome them, then the melting point and the boiling point will be much, much lower. So if we think about our metal, we just said there's this really strong electrostatic force of attraction between the positive ions and the delocalized electrons. So because it's really strong, it needs a lot of energy to overcome, and therefore metals have high melting points. Then if we think about the malleability, this comes down to these really, really regular rows that metals have. So basically, if I hit the metal on one side, then a whole row of positive ions can just move over the top of the other ones. And then the bonds just reform between the electrons that are there and the new ions that are in this new position. So that makes pure metals really malleable and really easy to change shape. And that leads us on nicely to alloys, which are mixtures where the major component is a metal. So in that, we've got atoms that are different sizes because different elements have different sized atoms. And so instead of having these really clean, really nice regular rows, the layers are distorted. So that means that if I try to hit it, they can't just slide over each other. And that makes an alloy much harder than the pure metal that it's made from. So then our second type of bonding is ionic bonding. So basically, when a metal atom reacts with a non-metal atom, then electrons from the outer shell of the metal atom are transferred. So the metal atom loses those electrons and it makes a positively charged ion because electrons are negative. So if you take them away, what's left behind is positive. And then the non-metal atom is gaining those electrons and making negative ions. So these ions are these charged particles made when the atom gains or loses electrons. So you can see here it's being transferred from the sodium to the chlorine. So it's always going metal to non-metal, left to right across the periodic table. Now, if we're trying to figure out how many electrons are moving, we're always working towards the point where the atom has a full outer shell, because that's a really stable way to be. So group 1 elements have 1 electron in their outer shell, so they're just going to lose 1. Group 2 have 2 electrons in their outer shell, so they're going to lose 2. And then if we think about group 6, like oxygen, they're 2 short of a full outer shell, which would be 8, so they gain 2, and likewise group 7 gain 1. So if you had a question where you needed to describe what was going on, you look at where the elements are in the periodic table. So I can see, oh, sodium here is in group 1, so it's going to lose 1 electron, and then chlorine is in group 7, so it's going to gain 1 electron, and they're always going to be given from sodium to chlorine because it's always going left to right across the periodic table. The one other thing to watch out for with this is just your language. So when you're talking about the ions, metal ions are easy. Non-metal ions, make sure that you've got "-ide" on the end. So you have a chlorine atom, but you have a chloride ion. You need to know that an ionic compound is a giant structure of ions. It forms this giant ionic lattice where we've got positive and negative ions in a constant ratio. So it doesn't have to be 1-to-1, but it's going to be the same the whole way through that lattice. Again, we've got a strong electrostatic force of attraction, but this time it's between the positive and negative ions. And remember, it's acting in all directions, so it's a kind of 3D force. Ionic compounds tend to be solids at room temperature because that force is so strong, so it needs loads of energy to overcome. And ionic compounds can conduct electricity, but only if they've been melted or if they've been dissolved in water to make an aqueous solution. There's also a little bit in the spec about some of the different models that we use for looking at ionic compounds. So the idea that, say, this 2D one on the left gives you the idea that this is a flat object, but it's not, it's actually in 3D. Both of these models kind of make it look like there's just a few ions involved, whereas actually we know that there are thousands and thousands of them. And this ball and stick model on the right isn't great because it makes it look like you could kind of reach out and touch the bonds, and that's not true. What's actually holding the thing together is this electrostatic force between them. The final type of strong chemical bond is covalent bonding. So basically, when atoms are sharing pairs of electrons, they make these covalent bonds, and they're really, really strong. So covalent substances could be small molecules, and there are 8 named examples that you need to be able to draw, but they could also be giant structures, and we'll get onto them in a second because carbon is one of the other major topics that we need to talk about, and a lot of the giant covalent structures are carbon-based. So these are your 8 named examples that you need to be able to draw. And every year that I've seen a question of this, what they've done is they've put the circles in there for you already, and then you just have to add in the dots and the crosses yourself. So you're not having to draw the circles in the exam. So we've got hydrogen, hydrogen chloride, ammonia, oxygen, chlorine, methane, water, and nitrogen. So first up, oxygen is an interesting one because it has a double bond. So you've got 4 dots and crosses together in that Venn diagram there. And nitrogen has a triple bond. All of the others, we've only got single bonds. So in every bit of the overlap, we want a dot and a cross. And then with the exception of hydrogen, which is in period 1, so it's only got that first shell, which only has room for 2 electrons, the way to kind of think about it for the rest of them is that you need to fill up until you have 8 electrons in total. And you get to count the ones that are inside the bond for both of the atoms that are sort of sharing it. One thing to watch out for, in about 2015, I think, they did put in a question that was a different one of group 7. So you're supposed to know that everything in group 7 is going to bond in the same way. So chlorine is the named example, but I think they put iodine in, and there may have been fluorine as well at some point. So just if you get anything from group 7, single dot and cross in the middle because it's a single covalent bond, and then 6 other electrons on each atom. So that's 7 in total that each atom is contributing. We also need to be able to explain the properties of these small covalent molecular substances. So the first one is that they are usually gases or liquids because they have very low melting points and low boiling points. So even at room temperature, there's enough energy around to melt them and maybe even boil them. So the reason for that is that the forces between these molecules are really, really weak. Now, the danger thing is people end up writing something about covalent bonds being weak, and that is wrong. Do not write it. Covalent bonds are super, super strong, but they don't have to break in order to melt or boil these substances. So within my water molecule, there are two covalent bonds. They are staying intact. That water molecule is staying together. The hydrogen is staying bonded to the oxygen. What is breaking is the weak intermolecular force, which here is my little green dotty line, between different molecules. The weak intermolecular force breaks, not the strong covalent bonds. The bigger that molecule is, the stronger the weak intermolecular forces will be. So you can kind of imagine it like for every atom there's a teeny tiny little force, and the more atoms are in the molecule, the more forces there are. That's kind of a good way of thinking about it, and we'll see that in a second with the polymers. The other thing we know about these small covalent molecules is they don't conduct electricity, because electricity or current is the movement of charged particles, and this molecule isn't charged. So there's nothing charged to move around, so they can't conduct electricity. Then we get polymers. So polymers are very long chains of repeating units called monomers. And you can see that I've underlined the word very because it's super important. A few years ago, there was a question where they asked you for a definition, and if you didn't say very, you didn't get the mark, which was really heartbreaking because loads of people wrote a perfect definition apart from that one word. So make sure you write very. So these monomers, they're not atoms, they're little molecules, but I've just drawn them as circles to make it easy. So these molecules, these monomers, have got strong covalent bonds between them, making up these really long chains. And then one chain to the next chain is held together with a weak intermolecular force. But because the chain is so long, and there are so many of these teeny tiny little weak intermolecular forces, they add up to kind of make quite a big force. And so polymers tend to still be solids at room temperature. Giant covalent structures are always solids because when we say giant, we're talking about usually thousands of atoms, and so they've always got really high melting points. So all of the atoms are linked to each other by strong covalent bonds. So whereas before we had 3 atoms in a water molecule with bonds between them and then weak forces holding one molecule near another one, here every single atom is covalently bonded up. So we've just got this massive structure. So in order to melt these things, we would have to break those really strong covalent bonds, and that's incredibly hard. So that's why all of these giant covalent structures have got really high melting points. Then also, one of the major topics for this exam is going to be structure and bonding of carbon, and most of the structures that we've got here are carbon based. The one that isn't is silica. So silica, or silicon dioxide, is made from silicon and oxygen bonded together, and then the other ones on this slide are carbon based. So firstly, you need to know about diamond. So in diamond, every carbon atom makes 4 strong covalent bonds to other carbon atoms. It's really important that you don't just say diamond has 4 bonds. No, it doesn't. Diamond has about 4 million bonds, but every atom inside diamond has 4 strong covalent bonds, and they're all carbon atoms, remember? So because of that, because of all those strong covalent bonds, diamond is very hard, has a very high melting point, and also it doesn't conduct electricity because there's nothing charged to conduct electricity. Then if we compare them to graphite, which is something the exam board love doing, diamond versus graphite, we've got carbon again. This is why they love it. It's a nice comparison because it's the same element twice, carbon and carbon. But in graphite, every carbon atom is only making 3 covalent bonds. So diamond has 4, graphite, each carbon atom makes 3, as that leaves us with a spare electron. So just like in metals, that electron becomes delocalized, it's allowed to move around and carry charge, and so it's just kind of going around through all these hexagonal rings here, and that means that graphite can conduct electricity even though diamond can't. You also need to know about something called graphene. So basically they took a strip of pretty much sellotape and put it on some graphite and tore it off, and we got just one layer of graphene. So a single layer of graphite is called graphene, and basically it's really useful because it can be used to make sort of electronic things and composite things, and you can bend it but it still conducts electricity, and it's kind of this wonder substance of the future. And then lastly in this section we have fullerenes, which again are made from carbon. So they are little hollow cages or balls or tubes, and they tend to involve hexagons, although sometimes they're heptagons or pentagons as well. The very first fullerene to be discovered was called Buckminster fullerene. It was named after this architect who made these geodesic domes. And also there are particular fullerenes called nanotubes, which are these little cylindrical tubes with a really high length to diameter ratio, and they're really useful in nanotechnology and making electronics and also material science. Quite a lot of quantitative chemistry is higher tier only, so there isn't too much here. So we start off with conservation of mass, which is this idea that you can't make or destroy atoms in a chemical reaction. And so that means that if you've got simple equations, they need to balance. So something like here's your photosynthesis equation, and you can see that there are 6 carbons on the left and 6 on the right, and that's Y. Also, this means that the mass of all of the products, so the chemicals that we're making, is going to equal the mass of the reactants. But they do like to ask you about situations where it might look like this wasn't happening, and this tends to be reactions that involve gases. So for instance, if you have a metal reacting with some oxygen, then you're going to make a metal oxide. And the metal oxide is heavier than the metal you started with. So it looks like the reaction is gaining mass, but really it's because before you started, the oxygen molecules were just floating around in the air and they weren't pushing down on your scales and you weren't weighing them, but they were there all along. It's just that we weren't taking it into account. And then likewise, if you've got a metal carbonate and you heat that up so that it splits apart, it's going to make some carbon dioxide and that floats off into the atmosphere. So again, it sort of stops pushing down on the scales, and then you just don't see it anymore. So it looks like the reaction is losing mass, but it's not. It's just that one of your products has gone away and you can't weigh it anymore. Next up, we've got this idea of uncertainty. So basically all physical measurements have some uncertainty because no instrument is 100% accurate, and the errors can be random or systematic. So we talked about those in the introductory bit at the start. We can talk about precision, which is basically how uncertain are you? So things like if your scales only weigh to the nearest gram, that's your precision, that's your absolute uncertainty. But often it's more useful to report percentage uncertainty, because say if I'm measuring the mass of something and it's out by a gram and the thing only weighed 5 grams in the first place, well, that's huge, that's really, really uncertain. Whereas if I was weighing 1,000 grams of something and then my measurement was out by 1 gram, then that doesn't really matter. So we take that absolute uncertainty and we divide it by the largest measurement that we're making, and then we times it by 100 to make it a percentage. Okay, so then we need to be able to calculate some relative formula masses. So remember, it's a mass, so you need to be using the mass number, or the relative atomic mass, from the periodic table. So say if I wanted to work out what the relative formula mass of sodium oxide was, well, in this chemical formula, I've got 2 sodium atoms, so I need the relative atomic mass of sodium twice, so 2 lots of 23, and then I've got 1 oxygen atom, so 1 oxygen would be 16, and then I add all those together and I get a relative formula mass of 62. Next up, we've got concentration. So there isn't too much of this that you actually need to know if you're doing foundation tier. You should know that a solution is where a solute dissolves in a solvent. So the solute is the thing like salt or sugar that's dissolving, and a solvent is the thing that it dissolves in. And to work out concentration, we do the mass of the solute, so the mass of the thing you're dissolving, divided by the volume of the solvent. And I quite like for this one that if you know what the equation is, then that gives you the units, or if you know what the units are, that gives you the equation. So you should know that that slash sign, that per sign, means divide. So very often if they ask you to work out concentration, they're going to give you on the answer line grams per decimetre cubed. So find the grams and divide it by the decimeters cubed. And the only way that can get a little bit trickier is if they give you the volume not in decimeters cubed. So if they did that, they would give it to you in centimeters cubed instead, and you would need to divide by 1,000 before you started. But even if you forget, that's usually only going to cost you 1 mark. The fourth unit is chemical changes, which starts out looking at the reactivity of metals. So you need to be able to describe 5 general reactions and also talk about using your observations, so the things that you can see in order to put metals in order of reactivity. So the first one is that metals react with oxygens to form metal oxides. So they could give you an equation and ask you to finish it off, like iron plus oxygen reacts to make iron oxide. Then the next one is that metals react with water to form metal hydroxides and hydrogen. So again, they could ask you to fill in an equation. And they could ask you about how you could use your observations of this to put metals in order of reactivity. So here I've drawn a little picture of some potassium with loads of bubbles being given off and some copper with no bubbles being given off. And so this would tell me that potassium is more reactive than copper because I've seen this more vigorous bubble production where the hydrogen is being made. Remember that if we wanted to prove it was hydrogen, we could set fire to it and it would burn rapidly with a squeaky pop sound. Then we need to have that metals react with acids to form salts and hydrogen. So you can remember MASH, metal, acid, salt, hydrogen. And you do need to be able to name those salts. So there are 3 strong acids that we know about at GCSE, and you should know their names and their symbol formulae. So if you've got hydrochloric acid, then that makes a salt called a metal chloride. So if we put sodium in hydrochloric acid, we make sodium chloride. Sulfuric acid makes metal sulfates. So if I put iron in sulfuric acid, I make iron sulfate. And then nitric acid makes metal nitrates. So if I put potassium in nitric acid, I'd make potassium nitrate. Then if we take a metal oxide, if you've learnt the MASH equation, just remember that the only difference between a metal oxide and a metal is it's got some oxygen shoved on it. So we take the same products and then we need to put that oxygen somewhere. So if you add that oxygen to the hydrogen, then we get water. Okay, so you're just kind of taking the same equation and then adding a bit of oxygen. And then the only difference between a metal oxide and a metal carbonate is one carbon dioxide molecule. So we've got the same salt, the same water, and now we've got carbon dioxide. And we could prove it was carbon dioxide by bubbling it through lime water and it would go cloudy. Okay, so here we've got our first required practical, and this is one of the ones that the exam board have said they are expecting to examine, so it's quite a good opportunity for a method question. It's come up a couple of times before where the first thing you've needed to do is identify what acid are you using and what base are you using. So there's only those 3 acids that I mentioned on the last slide, hydrochloric, sulfuric and nitric. So look at the name of the salt to work out which acid you're using. You need to heat that up, and you're heating it to make it react faster. Then you add a base. So the base could be a metal oxide or a metal carbonate. They both work. The only reason that you would have to go for one over the other is if they say use a metal oxide or they say use a metal carbonate. We add an excess, and that means adding too much, and you'll know you've got an excess when it just stops reacting and you see it kind of piling up on the bottom of your beaker or whatever you're doing the reaction in. And the reason you're doing that is that we want to make a pure salt at the end. So we have to get rid of anything that hasn't reacted, and it's way, way easier to get rid of extra base than it is to get rid of extra acid. So we add too much base to make sure all the acid reacts. Then we filter it to get rid of that excess base. So then you've got your sort of salt solution, and then we need to evaporate the water so that we've got crystals instead. Now you have to evaporate most of the water, not all of the water, because if you evaporate all of the water, you don't get nice crystals, you just get horrible white boring powder. And you're going to evaporate it using either a hot water bath or an electric heater, because they're going to sort of gently remove that water. A Bunsen burner would just be a bit too vigorous. This is just a bit from the spec about why metals are more or less reactive. So it's basically to do with how easy it is for them to lose electrons and therefore make positive ions. We've already said that you can use your observations to put metals in order of reactivity. Just watch out, if they say observations, it has to be something that you can see. Okay, you can't be talking about electrons being lost, because that's not a thing that you can observe and detect. And also make sure that you know carbon is more reactive than zinc and iron. And then less reactive than the others, potassium, sodium, lithium, calcium, magnesium on that slide. So that means that you can use it to extract zinc and iron, but you can't use it to extract those more reactive metals. And hydrogen is more reactive than the jewellery metals. So copper, silver, gold and platinum. Those 4 you're not going to have reacting with water, and you're not going to have reacting with acids, because hydrogen is more reactive than them, so they can't displace the hydrogen from water or acids. If you've got a really unreactive metal like gold, then we can just find it native as an element in the Earth's crust. If you've got a metal that's slightly more reactive, then we can reduce it using carbon. So that means react it with carbon, and the carbon will sort of take away the oxygen from the metal because the carbon is more reactive. So that's quite a good way to extract things like iron and zinc. But you can only do it if carbon is more reactive, so it doesn't work for potassium, sodium, lithium, etc. And you don't want to use it if it's a metal that carbon will react with, because then you would remove the oxygen from the metal, but you would just replace it with carbon, and you still wouldn't have pure metal, and you still wouldn't be able to use it, which would be kind of rubbish. Then we get a little bit about acids and alkalis. So acids are chemicals which dissolve to make solutions containing hydrogen ions. Alkalis will dissolve to release hydroxide ions. The pH scale goes from 0 to 14, so 7 is the neutral point at room temperature, and then 0 is very, very acidic, and 14 is very, very alkaline. If an acid reacts with an alkali, they form a salt and water, and then also that bottom line there is what we call the ionic equation. So basically it's the equation for an acid reacting with an alkali where we've taken out anything that's not part of the reaction. So we've taken out what we call the spectator ions. Finally, in Unit 4, we've got electrolysis, although quite a bit of electrolysis is higher tier only, so you don't need to know about the half equations and things. So electrolysis means splitting up compounds called electrolytes into their elements using electricity. In order for it to work, we need to have, we've got to start with something that's charged. So you can't do electrolysis if you have something that's not ionic. And the electrolyte needs to be either melted, so we're giving that lattice a lot of energy to break it up, or it needs to be dissolved, because if the ions can't move, then we can't have electrolysis. We call the positive ions cations, and the negative ions are called anions. So as soon as you turn on the electricity in electrolysis, then you're going to have the ions are going to start moving, and they're going to move basically. The rule is opposites attract. So positive ions go to the negative electrode and negative ions go to the positive electrode. And then we name those electrodes based on kind of matching up with the ions. So positive cations move to the negative electrode called the cathode, and negative anions move to the positive electrode called the anode. And when they get there, we say that they're discharged. So that means that electron transfer takes place and these charged particles called ions stop being charged and just turn back into their element form instead. We already mentioned that you can only use carbon to extract a metal if the metal is less reactive than carbon, and also if it doesn't react with carbon, because otherwise that would just be no good. So for more reactive metals like potassium and sodium and so on, electrolysis is the different method that we're going to use instead. So here we've got aluminium, because this is a really good example. So aluminium is manufactured by electrolysing this mixture of aluminium oxide, so that's a compound that contains aluminium, and it's mixed up with something called cryolite. So the cryolite is basically in there to break up the lattice and make it easier to melt it, because melting this is going to take a huge amount of energy, and that's going to be really, really expensive. And then for this electrolysis, our electrodes, these inert conducting rods, are going to be made of carbon, because carbon conducts electricity really well, but it's a lot cheaper than most metals, and it's relatively unreactive. But at the high temperatures that we're going to have to use to melt the aluminium oxide, actually even the carbon will end up reacting. So basically what we have is the positive aluminium ions go down to the bottom, and they pick up some electrons and turn back into aluminium, and they go out of that little tube to the side as molten metal. And then the negative oxide ions are going to go up to the positive electrode, which we call the anode, and they're going to give away some electrons, and we're going to form oxygen molecules. We're going to make oxygen gas. But those positive anodes are made of carbon, and so when you've got really, really hot oxygen being formed near carbon, it makes carbon dioxide. And so over time, the anodes get worn away, and so they have to be replaced about once a month or so. So this is a really expensive process because it takes a lot of energy to melt the electrolyte, and also it costs a lot for the electricity to actually make the ions move, and we keep having to replace the electrodes as well. The last thing in Unit 4 is about the electrolysis of substances that have been dissolved, so that we've got an aqueous solution rather than melting them. And this is a bit more complicated because now you have to worry about the water too. So as well as the two ions from the electrolyte, from the compound that we're actually trying to split up, we've also got hydrogen ions and hydroxide ions from the water, so an H and an OH. And so each electrode is going to have two different ions competing for discharge. So there's some rules to decide kind of which ion wins. So at the negative electrode, at the cathode, you're either going to make hydrogen or you're going to make a jewellery metal. So silver, gold, copper, platinum. Those are your only options. Now, unfortunately, you can't say in the exam, oh, if I'm electrolysing silver nitrate solution, I'll make silver because it's a jewellery metal. You have to say, because this is the less reactive thing. So for that example, I'd be saying silver will be formed because silver is less reactive than hydrogen. But if I tried to electrolyse some sodium chloride solution, I'd be saying hydrogen is formed because hydrogen is less reactive than sodium. So it's always the least reactive thing that is going to be discharged and made. Then at the other electrode, at the anode, if you've got a halide, so an ion that's come from group 7, so that could be fluoride, chloride, bromide, iodide, acetatide, that is going to be discharged and you're going to make a halogen. So if we've got sodium chloride solution, we'll make chlorine, and the reason why is because chloride is a halide, it's from group 7, so we make chlorine. If you don't have a halide, so if you have literally anything else, it doesn't matter, they could talk about nitrates, sulfates, phosphates, loads of things you haven't even heard of, anything else that is not from group 7, then you're going to make oxygen. And that happens because the hydroxide ions break apart, basically. And then our final topic for paper 1 is energy transfers. So firstly, we need to know that energy is conserved. We already had the idea of mass being conserved for unit 3. Now we're saying the same thing, but for energy. So energy can't be created, it can't be destroyed. At the end of a chemical reaction, we're going to have the same amount of energy that we started with. It just might be stored in a different place. You need to know that an exothermic reaction is one that transfers energy to the surroundings, and that will mean that the temperature of the surroundings increases. So that could include combustion, oxidation, neutralization, and that's really useful for things like self-heating cans and hand warmers. Then endothermic reactions take in energy from the surroundings, so the temperature of the surroundings will decrease. And this includes thermal decomposition and also the reaction of citric acid and sodium hydrogen carbonate. I know that's like a weirdly specific example, but it is in the specification. So they could name that reaction and then say to you, oh, multiple choice time, is it exothermic or endothermic? And you need to know it's endothermic. Also, a bit of biology crossover, photosynthesis is also endothermic because it absorbs light energy. And a good use for endothermic reactions is sports cool packs. We've got one more required practical to look at, and this isn't one where every school is going to have done exactly the same reaction. So you need to investigate the variables that affect temperature changes in reacting solutions, such as acids and metals, acids and carbonates, neutralizations, or displacement of metals. So it's unlikely that they're going to expect you to know exactly what reaction they're talking about. They're going to have to give you some information. But overall, the kind of general principle is the same. We're interested in the temperature change, so we need to measure the temperature at the start and the end and work out what the difference is. We're probably going to need to work out whether the reaction is exothermic or endothermic, or make some kind of conclusion about what makes the temperature change get bigger. So things like adding more metal or using a more concentrated solution or whatever it is. In order to get the best possible data, we're going to want to insulate the experiment, so do it in a polystyrene cup, pop a lid on top. And in order to get the best, most precise data with the smallest resolution, remember that's a good thing, it's being able to tell the difference between data that are really similar to each other, you're probably going to want to use a digital thermometer. This is a really good one for them to ask you about control variables to increase the validity. So things like if I was looking at different metals in acid, I would want to always keep the volume of the acid the same, the concentration of the acid the same, and the mass of the metal the same. Remember, amount is a banned word. You never, ever, ever talk about amount. You say mass or you say volume. Be really precise in your language. And make sure that if you are writing a method, that you remember to actually talk about changing the thing that they've told you that you need to change. And then the very last thing that we need are these reaction profiles. So basically, we're showing the course of a reaction from left to right as time goes on. We start off with the amount of energy that's stored in the chemical bonds of the reactants. We finish with the amount of energy that is stored in the chemical bonds of the products. And if the products have less energy than the reactants, this kind of spare energy has been given out to the environment. And so that makes it exothermic. So that's my one on the left. And then my one on the right, the products have more energy. Well, where did it come from? They took it in from the environment, which would have got colder. So the one on the right is endothermic. The pink arrow, it always goes from the height of the reactants up to the top. That's your activation energy. That's the energy that was needed for that reaction to start. So that's it for the foundation tier of Chemistry Paper 1 of AQA Combined Science. I really hope that that's helped you to feel a bit more confident. I am wishing you so much luck for tomorrow. Try not to get too stressed this evening. Just have a little look over your notes, particularly look at the required practicals, get a really good night's sleep, and then just go and nail it.